local resident John Day, who's been more distinguished but fantastic for judging the art of games in the past, has stepped out to reveal his true engineering self. So take it away, John.
Well, thank you, David. Really appreciate it. Thanks, everybody. So we can get the slides going, Jillian? That'd be great. So first off, everybody, thanks for spending the next hour of time. I promise you will not fall asleep. How's that? So my name's John Day. I'm a very serious pinball, collector, restoration dude. I've owned a pinball machine since 1985, which I had in my dorm room in college. So this is really taking me on a very interesting journey. Today, what I'm going to talk about is adding solid-state rules and capabilities to a traditional 1970s Gottlieb EM, and we're going to go over all the details. I'm on pin side. I'm a pin engineer 77. With that, we'll move on to the next slide. Thank you. So agenda. First off, exactly why would you add a solid-state controller to an EM? So I'm going to go over the reason why I developed this project in the first place, and then some of the objectives, like preserving the EM soul. I do a lot of restoration work on EMs and solid-state games, and I didn't want to just rip out the EM soul of the game. And I'll explain exactly how that's preserved, but yet adding solid-state rules. There are a lot of technical challenges. Pinball EM machines run on alternating current. They run on different voltages. If you're familiar with solid-state games, they're all DC. You cannot match the two, so you have to deal with interfacing between those two domains. Also talk about project phases. This phase started with just a bonus unit only replacement, and then later on, a second revision of board set was developed to do a full rule set implementation. That was the plan all along, actually. We'll talk about all the circuit implementations, so exactly all the circuits. We'll go into the schematics and how it stitches into the EM itself. And then we'll also, slides? And then we'll also go over the firmware development, so the software that is running on this game. And then, like everything, if you've ever developed, has anyone here developed electronics at all in their career? So I see a couple hands. Have you ever had a failure that you didn't expect? So we'll talk about that. So anyone who has ever developed electronics, you'll certainly appreciate some of the failures that I encountered. And then we'll go into a deep dive of the implementation and a live demo of the game. With that, we'll move on to. So the why, like why would you ever do this? Develop a hybrid EM controller. So I had two Target Alpha machines at the time, so I restored both of those. And if you've ever worked on a Target Alpha, has anybody worked on Solar City or Target Alpha at all? And Dave, I know you guys have owned them. And if you've ever worked on those games, you'll notice there's the bane of those games is something called a bonus unit. And it's this stepper unit that resides under the play field, and it basically scans all of the targets, whether they're down or not. And then that awards your bonus at the end of ball. And those units are notoriously difficult to work. They are unreliable. Sometimes they'll give you an extra 1,000 points. Sometimes they'll skip 1,000. It'll like give you a bonus, and then it will skip, bonus, skip, because it's basically scanning the targets. And it takes a long time, and you have to wait for the entire 15-target scan, even if you have no targets down. So it actually delays the ball time for the next ball. There's another real major problem that this game has, and that is when you drop the drop targets down, so good players, or if you have a good ball, guess what? You are actually have nothing to do. So you knock all the targets down, and now there's nothing to hit. You have this blank play field, and you're just like, okay, I guess I'll get extra ball and drain it because there's nothing else to hit. There's no points on the play field. And the reason for that is because the state of the targets themselves are actually how the bonus unit scans. So if it were to reset the targets, you would actually lose the context of the bonus for those targets. So it wouldn't be able to give you a bonus if it reset them. So the only way to really solve this is to do a full solid-state controller, or you'd have to add a ton of EM logic. So I chose the former of the two. Next slide. So here are the design objectives. And first thing I wanted to do is maintain the soul of the EM. It could have been really easy. I could have just ripped out all the EM stuff and then just done a standard off-the-shelf, like fast pinball controller or whatever. That is not this project. So I wanted to really retain everything: relay, boards, score, motor, all the relays, player unit. Everything is totally intact and working on this machine as original. Also want to make sure that the modifications are easily reversible. This game could very well outlive me. I don't know. So there may be some future owner that maybe wants to bring the game back to an original EM. I have no idea. But I wanted to make sure that all of those modifications could be reversed at some point if that was ever desirable by a future owner. So we only just remove the bonus unit, and obviously I have that. And then all of the interfaces are just anything that's changed, and I'll explain what's unsoldered and then what's put in its place was all designed to be very easy to reverse that and bring it back to its original form. But this drastically enhances gameplay. So now you get target reset during gameplay, just like you do with El Dorado. You get unlimited bonus now. So you could have 50,000 bonus if you want to, if you hit 50 targets down in that particular ball. You have things like target hunt now. So you have skill shots that are available, and those are worth more points. Those are things that can be added to the game. You have much faster gameplay because now you don't have to wait for the bonus unit to scan for targets that aren't even down. So that's sort of another enhancement that you get as well. And we've added some other things. There's a vacuum fluorescent display that was added in the lower right-hand corner. It can give you some rule guide information, and also like the high scores and all that kind of stuff, or not the high scores, but the free play scores are listed there as well. And then also you get a track mode. EMs are kind of a little boring, when they're just sitting there. The lights are on and that's it. And now you've got all kinds of animated light shows and such that you get in the solid-state games, and obviously you get that here as well. So next slide. So there are some interesting technical challenges. So the first is that modern solid-state games, they have a common ground. And so anyone here restore a solid-state game? So I was hoping to see a lot of hands. That's great. So you're familiar with, you have common ground. You'll have 43 volts if it's a Bally. You'll have a 12-volt power supply, and then you'll have a down regulator to 5 volts in a typical Bally solid-state game. Gottlieb's are like 28 volts DC, but it's all the same, and there's a common ground. But with an EM, that's not the case. With an EM, you have 25 volts AC, not DC, and then you have and that's for all your solenoids, and then you have 6.3 volts AC, which is for all of your lamps, which are both insert lamps and also your GIs. So the microprocessor, which runs on 5 volts DC, that has to be able to transition from sensing a 25 volt AC signal. It has to be able to sense if that's there or not. And then it has to translate that down to 5 volts so it can sense it. And then you have to take 5 volt outputs and bring that back to 25 volt solenoid signals or relay coil signals. We're all at 25 volts AC. So also you cannot have a common ground. So the ground of the microprocessor is actually riding up and down on the AC waveform of the EM. So there is no actual common ground, and I'll show you in the schematics of how that's implemented. So to get to AC inputs, I used optocouplers, very similar to the optocouplers you might see on a DMD game. And then to get from the DC domain back to the AC domain, I used 5 volt relays. And so there's a bank of 8 5-volt relays in the system, and then there are 2 optocouplers in the system as well. So next slide. So this is the AC power supply, and it's pretty straightforward if you're familiar with any standard solid-state game. This is a 6.3 volts GI lamp, and there's just a standard bridge rectifier. It's implemented discretely, you can see there. And then that is using a MIC 29300. That's a 3 amp low dropout regulator. Not that different than the 7805 class game regulators you'd see on a Bally solid-state game. This one has very low dropout voltage, because when you rectify 6.3 volts, you actually lose like 1.4 volts. You're already down to close to 5 volts at that point, so you need really low dropout on that regulator. But that's about it. So the power supply is pretty simple, and that's just connected to the 6.3 volts winding of the EM transformer. So the transformer has a 25 VAC and a 6.3 volt winding, and it's just connected to that winding at the relay board. So then there's the optos. So this is the way that, let's say, for example, it has to sense if the game has tilted, it has to sense when it is the last ball for double bonus. So those are two of the sensing signals that are required. And those are at 25 VAC. And so, so there is basically a circuit which is basically a diode, a series resistor, and kind of a load resistor. And what that does is that turns on the LED of the opto, and then in the 5-volt domain, the microcontroller can then sense the photodiode and then see whether that photodiode is actuated or not. And this is one of the things that was not actually very obvious. Like when I was first doing the firmware development on this, I was actually getting unreliable results. I was like, hey, this signal's kind of coming in and out. Why is it doing that? The game's tilted, so why is it telling me it's tilted and it's not tilted? And what I failed to realize when I was first doing the firmware is it's AC. So it means that the opto is going on and off at 60 hertz. So if you looked at the signal, you would see it would be on for, for like maybe 7 milliseconds, and then it would be off for 7 milliseconds, and then on. So I had to realize that, so I had to change the firmware to be able to deal with this pulsating 60 hertz input in order to be able to detect those inputs. So just some of the weird things, like, you're used to dealing with DC stuff, and you suddenly realize that you have to contend with some of these, these AC domain issues. So pretty simple. So then the DC to AC interface, so which is, how do you get back to actuate a relay or actuate the target bank reset, for example. That's implemented with 4-bank standard 5-volt DC relays. And so these are normally open contacts. We bought them in banks of 4, and those were rated. It's kind of interesting. So you buy these relays out of China or whatever, like AliExpress and such, and they have all these great ratings, right? 250 volts VAC at 10 amps. So you're like, hey, I'm in great shape. I'm only doing 25 VAC, and it's maybe less than an amp for triggering a typical relay coil. And the target bank resets, those are 125 VAC, but those are at maybe an amp and a half. So you're well below the official rated current of those relays. But I'm going to share something with you in a few minutes, and that is those relays failed anyway. And so we'll talk about that and maybe how that was mitigated. So the relay outputs, these boards are pretty cool. They have isolation. I didn't use that. But they do have status LEDs, so you tell when the relays are asserted or not. And then here's the 8 signals that you have to connect to. And so it is the tens relay, so that's the L circuit. There is the hundreds relay, which is the M relay, if you're familiar with that in the head. And then the thousands relay, which is the N relay. And then there is a extra ball signal that you have to connect to in order to latch the extra ball condition so that you won't advance the player unit. And then there is another solenoid that you need to actuate for special if you want to give the player an extra game. And then there are some other additional outputs that you need to deal with. So the magic of all of this is that this EM, the solid state controller, intercepts the ball trough switch. So if you're familiar with EMs or Gottlieb EMs, there is a ball trough switch that the ball resides in, and that's what kicks off the score motor to advance the player unit to the next ball. And that is intercepted. So the microprocessor is scanning that switch now, and now there is a relay that is in the relay board that will assert that switch locally. So now the microprocessor can do whatever it feels like. The ball is drained. It can do animation for bonus. It can tick off all of your bonus. And the EM thinks that the ball is still in play right now, actually. And then when it's done, then it kicks off the ball trough relay. And then that now causes the score motor to advance, player unit to advance, and now the game moves on to the next ball. And the last two, which are super important and one of the major reasons for this controller in the first place, is to be able to reset the 5-target and the 10-target bank. And I'm directly controlling those, so those solenoids are in direct control of these relays. You can reset them at any time you feel like it. So there were a couple phases of this project. And if you're familiar with engineering, a lot of times it's always a good idea to do proof of concepts and sort of break a problem down into multiple phases, because sometimes if you tackle the problem, the whole thing all up front, you may be discouraged, might be a little bit too much to So we always plan on things like revisions, Rev A, Rev B. This was a phase 1 and a phase 2 of the project. So phase 1 was basically bonus unit only. So the objective there was to eliminate the mechanical bonus unit, implement a solid-state controller, and then play the game and just see, does it fail? Does it have reliability issues? I mean, how well does it work? Like, what do you learn from that? So that was the whole objective there. So that was a custom board. I'll show you what that looks like in a minute. It was powered from the GI circuits, and then there were there was one onboard opto, which was used for the scanner. If you've looked at like a Target Alpha, the original bonus unit, there's a solenoid that advances the 15 positions, that kicks that, it's basically a stepper unit, so steps through it. So that particular solenoid input is the opto input for that controller, so it knows when the relay board is advancing to the next target. And then there was 2 other relay outputs, so there's the opto input and the 2 relay outputs, and those emulated the switch contacts that you had that it was scanning, and they emulated the 15th position. On that bonus unit, there's a set of switches that you'll see, switch contacts, and when it hits the 15th position, they get closed, and that's what causes the game to finish bonus and advance to the next ball. So there's a relay that basically emulated those contacts, and a relay that emulated the wiper that is wiping across the 15 positions. And that was it. So that actually improved the gameplay quite a bit. So this proved out power supply, the AC to DC domain, and DC to AC domain. So it kind of proved out all of those circuits. And then it made a significant improvement in gameplay because, like, it was cool. Like, let's say you have a bad ball and it drains. And if you ever play that game, by the way, it sucks because it drains and then it goes for 15 positions. It's almost like it's making fun of you, and it's like, dude, I just want the ball to come out so I can play another one and hopefully better next time. And so it eliminated that issue, like, right off front. So, like, if you had no targets down, the score motor wouldn't even spin. It would kick the ball out and then just spin to advance the player unit, and that's it. So it was much faster game time. It also eliminated the bonus count was completely contiguous. So if you had like targets, if you're familiar with the way the scanning works, it's done in a linear fashion. So you might have some targets down, some targets not down. And so in the original game, it would go, bang, bang, and then it would do nothing because you don't have any targets down. And then all of a sudden, bang, and then bang, bang, bang. It's almost like it was doing Morse code sometimes, So it eliminated all that. So now when it decided it was going to dispense bonus, it would just bang out the bonus all in a linear fashion, regardless of where the targets were that had fallen. It's guaranteed that you didn't miss any bonus because it's dead on. So there's no more like missing bonus or getting an extra bonus, which again is common in these games. And then it would eject the ball basically after every 5 targets down, which was really nice too. It eliminated one extra 1/3 score motor spin as well. So I actually had 2 Target Alphas at that time, and I had another friend who's not here actually, but he had a Solar City. And we converted those 3 games to run this bonus unit hardware. And we wanted to run it for a while, see if there'd be any failures. So we kept that in the game for about 2 years. And they worked perfectly. And in fact, one of those Target Alphas is out in the wild. I've lost it. It's been sold to 2 or 3 different friends. I don't even know who owns it now. So someone owns a game with this bonus unit in it. It's a one of a kind. I don't know if they're in this crowd right now, but it'd be interesting to see who owns it these days. So next slide. This is the bonus unit schematic. And just to go over this briefly, this is a AC to DC power supply, very similar to what I showed earlier. And then there's a single scan opto, so you can see that opto that's implemented there. And then there is the score and 15th position relays. You see those 2 relay outputs there that emulate the switch contacts and emulate the wiper scanner, essentially. And then there are 15 DC target switch inputs, and you can see those down at the bottom. And those all connect to a microchip. It's called a PIC16F. I think it's a 15345. So full disclosure, I actually work for Microchip, so as a apps engineer, so I kind of I guess I get the tools for free or whatever. So I've got a lot of experience with these parts too. So anyway, so that was really a fun project. Got that up and running. Ran for about 2 years or so. And then at that point was starting to really plan out the next phase once I had some good confidence that this was a solid way of dealing with an EM. So next slide, you'll get to see some pictures of it. So I used a tool called KiCad. Anyone here use KiCad at all, do board designs? So yeah, it's an awesome tool. So this is all done in KiCad. It's a free tool. If you ever need to do a PCB design, highly recommend it. It's called KiCad.org. And then if you look at the next slide, you'll see it actually implemented in the game. And it's kind of cool, like the 3D pictures represent what the real thing is, which is kind of fun too. But to show you some of the wiring here, you'll see the 6.3 VAC, so that just connects to a GI lamp, for example. And then the scan, that's the solenoid that would increment the stepper. That's just that solenoid connection. And then you see the relay connections, and the upper one is the 15th position. Those are all the wires for the switch stack that's at the 15th position when it hits the end of scan. And then the lower one is the 2 contacts. That's what represents the wiper contacts. And then you have your 15 targets you see at the top. So that's what the wiper contacts would have been connected to. And you'll see that those are connected there, which is pretty simple. So you can see how this is not really that invasive in the game. You know, you can see they just tap on the 6.3 VAC. The bonus unit's removed, but the wires that were connected to that now connect to this board, and then same with the switch stacks are connected to it as well. So that was phase 1, and then at that point we kind of moved on, or I kind of moved on to phase 2, which was a full hybrid with custom rules, and this was really where I wanted to take the project in the long term. So now I got a lot of confidence in the circuits. You learn a lot from implementing like a Rev A. You kind of learn like what you do differently, and so now that you've got that experience, it's time to move on. So in this particular case, I ended up deciding to do a single printed circuit board design that could be used for both the play field and also for the relay board. And I'll explain that architecture in a minute. But one of the things, if you look at a lot of modern games, like a Stern, you'll see that there's a data cable, basically, that connects between all the spike boards. So I implemented something very similar. So there's a simple RS-45 data cable that goes between the play field and the relay board itself. And that really reduces the number of wires. Cabling's nice and simple, very easy to diagnose. And there was some significant advantages when writing the game code, because now the real-time things like asserting a relay, where let's say if you asserted a relay or you turned on the solenoid to reset the drop targets, if you halted the code or the code went haywire, the solenoid would burn. And so this eliminated all that, because now there's a separate microcontroller that is doing nothing other than managing all the relay timing. And so you can now develop all your game code on the primary playfield microcontroller, and now you can halt it, you can screw up the code, whatever you want, and there's no risks of causing your game to catch fire. So I think that's pretty important. So it was a single PCB, and that was done mainly because it saves me some cost. That way I get the PCBs manufactured, and I can just populate them differently based if it's playfield or if it's the relay board, and I'll show you that in a moment. 45 between them. Used an old USB cable. So I don't know if you've ever cut the ends off a USB cable, but it's a nice data cable with power. So just reuse that. It was perfect. And then the playfield controller scans all of the switches. It drives the RGB LEDs, so for all of the animation and such. And then it has a apron display, which we'll show in a minute. And that shows you game status and has like a track mode type of information, where the replays are set, all that kind of stuff is there. So, and the relay controller itself contains the DC power supply. We'll go into the details of that in a moment. Scans all the AC isolated, which is tilt and ball relays, or last ball, which is basically ball number 3 in a 3-ball game, and drives all the relay outputs, and also provides all the timing. There's also a place for a MP3 player that's there as well. And so I do plan on adding MP3. So we'll have a speaker in this game and be able to play background music and all kinds of call-outs and stuff like that. So if I return in April, I would expect you'll see quite a few modifications and enhancements by that time. So this is the playfield controller. And the main microprocessor is an Atmel microchip. It's called a SAM C20, which is it's a 256K ARM M0 Plus part. Runs at 48 megahertz. Way overkill for this application. So it's totally overkill, which is appropriate for an EM, right? If you're going to put a microprocessor in, you should put a big one in there. And so it basically scans the 10 drop targets that you see in the upper part of the playfield. It scans the 5 lower drop targets, so those are all just direct signals into the microcontroller. It has pop bumper and stand-up switches, so it can see if the stand-up switches have been hit by a ball or the pop bumper is asserted. It scans the rollover switches on the left and right for special and extra ball. And then it's scanning that ball return that I mentioned earlier. Has the ball returned, then it knows that the ball's no longer in play. It can dish out the bonus, so it can send out the bonus, do animation, whatever else it feels like. And then when it's done, it can close the ball return relay at the relay board, which will then advance the player unit and continue the game. So it also has some outputs, too. There is a UART, which is the display UART in the lower apron. And currently, I'm not doing a ton with that. That has some statistics, some internal variables when the game's in play. It tells you the scores are required for a replay, typical stuff that you would have hard-coded on a game. There's some rule, sort of in track mode. There's some rule suggestions that you might see there as well that pop up. So I think there's an opportunity to do more there. And then it also drives the WS2812B LEDs. So that's how it's doing all of the color generation for that. And then it's got a RS-45, which is basically that USB-style cable, but it's just a standard serial cable. And that connects to the relay controller, which I'll show next. And the relay controller, you'll notice that the printed circuit boards, the layout is the same. You'll notice they're populated very differently. So you'll notice on the left, you'll see like the 15 pins up top. I'll show you the details of that in a minute. But you can see how the connectors are populated differently. You might notice a couple jumper wires that are in there as well. So I kind of designed it so I could just repurpose this board for both purposes, which kind of helped in some of the manufacturing costs. So, and now this is the relay controller. So this controller, playfield controller was mounted to where the original bonus unit was. The relay controller is mounted down on the relay board next to the transformer. So that's down there. And the relay controller itself has 2 inputs. Those are AC, so they have to be optically isolated. And that has to know when the last ball is occurring so that it can properly show double bonus. So that's really important. It also needs to know if the game's tilted or not. That's useful information also. So it needs those 2 bits of information from the relay board in order to make some decisions. Then it also has, it connects, you can see, through 485 to the playfield controller. And so that we showed in the previous slide. And then it has outputs. So first off, you'll see the 6.3 VAC lamp circuit, which is the power supply. So that's how it's generating 5 volts, and where all the 5 volts is available for the playfield as well. And then that also contains the 8 relay outputs that you see. And you can see, 2 sets of 4. And just to review those one more time, it's, the N, M, L, which are all your scoring. Those all go directly to the head. And then it's, ball return, 5-bank reset, 10-bank reset, and extra ball and special. So those are all your relay outputs, and that's it. So these are the detailed pinouts or pins, connector assignments, just to kind of make this presentation complete. And we'll start on the left with the relay board. And what you'll see on the relay board is you'll see the chip all the way up here on the right is a RS-45 transceiver driver. And you'll see the 4-pin connector that connects between the playfield and the relay PCB. And then you'll see a last ball and tilt. Those are the 25 VAC signals to know when the game's tilted or if it's in last ball mode. So those go through the optos, the opto isolators that you see there. And then there's the 6.3 VAC, which is the 5-volt power supply. You can see that regulator down there. And then there's 2 connectors, which have 4 outputs on each, and each of those drive the relay boards. So those are your 4 outputs for the relay boards that map to that. There's another connector. It's not shown populated here, but it is on my game, which does the apron display that you see. And you'll notice a USB connector. Like, why would you need a USB connector? And the reason is because we have plans to be using a DFR, I think it's 299, which is an MP3 player. So we'll be populating that, writing some firmware drivers for that. That'll give us the ability to do call-outs and speaker and do all kinds of fun solid-state music, whatever else we decide to do there. So that'll be fun. On the right, you'll see the playfield controller. And so the playfield controller, again, it's the same PCB. You'll see that the regulator's not populated. A lot of stuff is not populated there. It doesn't need the opto-isolators. But same microcontroller is there. But now, all of a sudden, the 15-pin drop target connector is populated. And then you'll see the driving to the RGB insert LEDs. And so that's where the RGB inserts are connected. That's where, the 45 interface is in the upper right. And then this is where the stand-up targets connect, and the rollovers and pop bumper input switches connect as well. And that's it. That's all the hardware. So that's involved for this. And this is the actual playfield. We're gonna get some cameras in here that can show some of this stuff live. But this is just a quick snapshot of the playfield controller PCB mounted. You can't really see it very well, but this is that 15-pin connector that was originally to the bonus unit. So it's connected down there. And then you'll see the pop connector, for the pop bumpers and stand-up targets there. That connector there is for the WS2812, so that's your RGB LEDs, and then same for up that connector as well. So pretty straightforward, actually. So, and next slide, thank you. It turns out that the inserts needed some custom boards too. Once you start designing boards, sort of your life becomes designing boards, it seems. So, once you may as well keep going, right? So. There is 2 different sets, and unfortunately, Gottlieb did not use the same spacing between the 10 bank and the 5 bank. May not be very obvious to you, but it will be after this seminar now, and you won't be able to unsee it. But it turns out that the top 10 actually have a 1-inch spacing, and the lower 5 have a 1 1/4-inch spacing. So I had to do 2 different PCBs. So you'll see the 1.25 PCB. And that you remove the lamps, and then you just screw that PCB down, and you're up and running. Very similar to the way a modern Stern game would implement it. And then you'll see the 2 PCBs at the top, which they're in series, and those represent the 10 drop targets there. And then there's a bunch of single insert RGB LEDs, and those go under the extra inserts in various places that you couldn't really have them co-located. So, and this is the actual series drive of it. When you drive these LEDs, you send a data packet out, and that data packet is formatted where you send the data for the last LED first, and then it just gets serially sent to each LED down the line, and that's how it works. So you have to know what this order is in order to get the programming correct, in order to get all the right places. And this is how it's wired on this game. So it goes to the 5 target first, then the 10 target right, 10 target left, then extra ball left and right, and then special, double bonus, and shoot again. So those are all of the inserts that we have RGB control over, which is pretty good, and I think it actually might exceed what a modern Stern has, because I think a modern Stern has 13 RGBs, so I think there's more than that on this, which I think is kind of hysterical, actually. So with that, we'll move on to the next one. This is the actual schematic itself, and so again, you'll notice that power supply is kind of carried forward, that you'll see in the upper left-hand corner, just from the original, bonus unit, phase 1 implementation. So that just got carried forward. Same thing with the opto-isolator, that got carried forward as well. You'll see the same target inputs. You'll see in the lower left-hand corner there that all go into, microcontroller inputs. And then you'll see in the upper right-hand corner, that's the RS-45 driver chip. That connects to a UART connection on the microcontroller. I have some relay stuff that you see there. Those relays weren't needed So I kind of envisioned that they would be needed, but in the end decided they weren't even needed, so they were never populated in either of these boards. But they're on the schematic. They're listed as do not populate. And then you've got outputs to like the WS2812B, and then you'll see the MP3 player at the bottom that we have a place for it, and expecting to kind of work on code on that probably this winter. So pretty straightforward. Not a lot to the schematic there. Take a look at it. It's not really there's really not a lot of active components. It's just the microcontroller, a regulator, and a RS-45 transceiver, and that's the whole thing, really. So there's not much to it. So let's talk about how you connect to what. So now you've got the PCBs, you've got the RGB LEDs, but how do you wire it all together? So we'll talk about that next. And so first thing, the 15 drop targets, the stand-ups, rollovers, pop bumpers, all that stuff, those are all disconnected from the playfield. So anything that is a switch input, like the drop targets, a rollover, pop bumper B relay, the original connection is unsoldered, put some heat shrink tubing on it, and then zip tied it. So it's still there, no wires are cut or anything. But the solid-state controller has to own those, because you've got to bring it into the DC solid-state domain. So all of that is disconnected. So there's roughly, I'm going to say like 20-ish or so connection points that you have to unsolder and then solder onto wires. And in some cases, you've got to run your own wires, essentially, to those switches. All the insert lamps were removed, and then the RGB boards that you saw were just screwed down in their place. And then next thing, then you're done with the playfield, believe it or not. That's all that's involved. And then now you pop the relay board out, and then you have to connect the L, M, N, extra ball, and special relays. Those are all in the head, actually. So there's a wiring harness that goes into the head, connects to those relays directly. And then you have the 5-bank reset, 10-bank reset, and the ball drain, the trough switch. Those all are on a Jones plug that you have on the relay board, so you just tap into those. And then lastly, you just connect to the 5-bank and 10-bank, which are on the Jones plug as well, and you're up and running, and that's it. And the 6.3 volt AC, which is right there at the transformer. So that's all the connections. So on the relay board, there's like no wires cut whatsoever. You're just kind of tapping onto the existing nodes that are there. And then in the playfield, there's roughly about 20 connections that were disconnected, and wires were provided separately. So with that, this is what the relay board connections look like. So you can see the board there that's mounted, and you can see the relays, the 2 sets of 4 relays. And you can see some of the wires that sort of go along there. You can see a couple of them that tap off to the Jones plug on the 5 and 10-bank solenoid connections. And then the last ball relay is the one in the lower, you can see that in the lower right-hand corner. It just connects to the relay coil itself, just taps right on top of it. So it can monitor if that coil's energized or not. So it knows the state of the game. And that's it. And in the head, connections are very straightforward. There's a relay common in one of the Jones plugs. So you just kind of tap onto the soldering point of the Jones plug. And then same thing with L, M, and N. Those are all available on Jones plug connections. And then in the case of Target Alpha and Solar City, there's a jumper where you adjust between extra ball or special. Turns out those are the places that trigger those solenoids or relays. So all you have to do is just connect to those, and you're up and running. So this is what the playfield looks like underneath it after it's completed. So you'll see the controller board there, which is where the bonus unit would normally be mounted. But you can see all the original EM wiring. All that stuff is all there. Nothing's really removed. And if you look at it closely enough, you can start seeing where the RGB boards are mounted, underneath the inserts. And then if you look at it even closer, you might see situations where the EM wires for the switch are disconnected, and then you can see a couple of wires that are brought in its place so it can scan it. But that's kind of all that's involved. And Dave suggested that we go into EM. Who here reads EM schematics regularly? Oh, I love that. So I guess that's why we're all here. So this is the Gottlieb EM schematic for a Target Alpha, and I just want to show the points where things are tapped in. So you can see that for the 10 and the 100 point, you just have to connect to, the common hot that's energized when the game is ball in play and not tilted. And then you just connect to the other side, which is the relay itself. So in some cases, you're just going straight across a switch, like there's a 1,000-point switch on target alpha. So you just have to get across that switch. You're up and running. In this case, I just got it all at the head. Because at the head, the playfield, you might remember on these games, there's a smaller Jones plug from the playfield directly to the head on these games. And that Jones plug contains actuation for like the tens, the hundreds, and the thousands. So I'm just kind of stealing. I just connect right to the heads. A lot easier to get to it there. And then you can control each one of those relays. So that's your 5s, 10s. I think the thousands the same way. I just ran out of space on the slide, but it's done the same way. And then with extra ball and special, those are, oops, I'm sorry, go back one slide. Thank you. So with extra ball and special, same thing. Those are available on the head. So there were tap points that were available. And that just shows you where those are tapped in on that Jones plug. And then again, they get to the common power when the game is on and ball in play is valid. So. And then next slide. And the last is you have the 5, and not second to last, that is. You have the 10 and 5 bank drop target reset relays. So this is 110 volts. So this is probably the most dangerous part of working with something like this because this is line voltage now. And so in this case, I actually did disconnect. I wanted to make sure that like the score motor was no longer powered and I didn't have to worry about like backfeeding or anything like that. So this is one situation where I disconnected the 110 from the path going to the score motor because I didn't need it, and then just biased these relays off of that and then connected directly to the Jones plug because the Jones plug itself has to provide 110 to the playfield in order to actually actuate those solenoids. And so I just tapped right onto the Jones plug, disconnected it from the score motor, which is what would normally access that, and then the relays now take over that connection. So, and then I think there's one last thing, which is ball return. And as I mentioned earlier, the bonus unit's removed, right? It's not there anymore. And it turns out that ball return is a lot of that complexity in this schematic. That are all those 15th point switches that the 15th position switch I mentioned earlier. That's part of your ball return mechanism. And so when you remove the ball return mechanism, you're sort of removed all of the connections to that already. So it was quite easy to just tap onto the net result of that at the Jones plug and be able to emulate the ball return. So, and then the last thing, oops, one more, sorry, back. So the last ball and tilt opto isolated inputs. So these are just optos that you have. They connect directly to the tilt hold relay and the last ball relay. So you just tap onto there. Now you know when it's last ball. You know when their tilt occurs. And that's it. That's all the wiring for the game. And this is the firmware development. So this is a MPLAB X IDE and a C compiler that works for the ARM parts and a simple snap debugger. And basically all the code was developed with that. And so, it's a standard IDE. The code's all written in standard C. It's 100% like ground up, so it's just something that I wrote myself. I have a do you mind if I introduce you? So I have a co-developer in the audience here, Dave Henry. So you might notice that there is a Solar City that is next to where the target alpha is. And we converted Dave's game in the last month, so we'd have 2 games here. And Dave's actually helped me with some of the cool new rules as well. So the two of us are going to kind of co-develop the code going forward. So anyway, so that's the IDE that we use for all the source code development and stuff like that. This is not based on any like standardized game platform whatsoever. It's a pretty one-off, unique thing. So that's it. And I think at this point, let's talk about failures. So the game was running for about 4 months. Like I got this game running in, I think it was January of 2022, so roughly a year and a half ago. I was so excited. Like it actually worked right off the top, like perfectly. And I played it. I was having a blast with it. And then all of a sudden, like the hundreds weren't scoring all the time. Like, I'd be like, wait a minute, I should get 300 points there, and I got like 100. And then it would like not score anything, and then it would score it some days and not score it others. Then the 1,000 points started doing that too. And I'm like, what the heck is going on with this? And the controller was fine, and then put some scopes on it. I'm like, I think these relays failed. But why would they fail? You know, I mean, they're not really loaded much. So I had the M and the N relay both start giving me trouble after maybe about 4 months, probably maybe 500 games or something like that. But the load is only 1 amp at 25 volts. But the relay says it's good for 250 volts at 10 amps. So why are these relays failing? I mean, I'm only using them at 10% of their rating. So I actually disassembled the relays, and this is a microscope picture of it, and the contacts were burned. So that's why the relays weren't working. And here's one of the interesting problems that I just had never thought about. And everybody familiar with the flyback diodes that you have on solenoids and relay coils? And if you know the reason for that, I'll just explain in a minute the physics why you need those. And that is when you energize a coil, whether it's a solenoid or a relay coil, there is a magnetic field that surrounds that coil, and life's good when you energize it. But the problem is when you de-energize it, the coil collapses. That energy collapses. And what it does is the coil does everything it can in its power to keep that current flowing. And what does that mean? It generates whatever voltage it can to do that. It's how your ignition system works in your car. That's how your spark plugs work. They're just a coil. It gets fired, and the magnetic collapses. It'll generate 30,000 volts if it has to keep that current flowing. So that's why diodes are added there. So the diodes are basically called flyback diodes. And what they do is they short that voltage out because it's in the opposite direction. That's great. That works in a DC system. But in an AC system, you cannot put flyback diodes in. That's not an option. So instead, I did some research and ended up putting an RC snubber circuit. And it's in this game. So far, I think this game has exceeded the failure time of the latest failures, but I don't know that for sure. We'll see if it makes it all through Pintastic without relay failures. So, but there are RC snubber circuits that we added to each of the coils. I didn't want to do that for the really high voltage coils like the 110, so I put a MOV there, a metal oxide varistor, which is the same thing you have on your typically on your line filter. If you've ever taken apart a solid state game, you'll see a MOV there. So that was it, and I think we're probably on the last slide. So at this point, I'd like to move on to a demonstration, and I'm just going to, if we can get the screen switched, that would be great. Thank you. And so everybody can see a track mode that's happening right now. So you can see all the lamps are flashing. You can see that we have display information in the lower right-hand corner. So that's pretty good. So now we'll hit reset. And you can see this is a standard EM. It's doing all the standard reset stuff that you would see, score motor spinning, all that kind of stuff. I'm not a good enough player to do this accurately, so I'm going to probably use my finger to show off some of the features. So first thing that you'll see is a flashing blue here, and that's indicative that this is a skill shot. And so if we hit that skill shot, that's too funny. There it is. And that's funny. Okay. So I missed the skill shot. Yeah, there we go. And so now it's reset, and you'll see that target resets after the 5th target drops. And now you'll see the extra ball is flashing. And so if we hit that, so now I'll get extra ball flashing here, and this is actually going to energize the extra ball. And now we're going to drain the ball. And you can see an animated bonus. So everybody see how the targets all turned green there. So you saw everything turn green. So now I'm going to try to get this correct. So now you'll notice that I got the skill shot now. So now this is turned blue now instead of red, or it was purple, I guess, before. And we get a second skill shot, which is pretty cool now. So now I'll hit this second skill shot. And now we'll get a third skill shot. So we can now hit that third skill shot if we wanted to. And it'll continue on. The skill shots continue on where you're getting an extra, I think it's 4,000 points. Is that correct, Dave?
2,000 for the first, 4,000 for the second, and then 2,000 beyond.
Oh, there you go. So that's the rule. So thank you. And so I think I'm only going to get, so you'll notice you get the 300, and you'll notice I'm getting 2,000 points now for the skill shot. So now let's say I screw it up. So it's down here. Notice it's moved from the upper playfield now to the lower playfield for skill shots. But let's say I screw it up, and I knock this one down. And so now it's over. So the skill shot's done. I only got 300 points for that. And now I'll drain it. And you'll see the animated. So now let's show some other things. So now I'm gonna just. So now I just did a sweep. So every target was now. So try that on a regular EM. So we got all 300 points for all 10 targets. We got 3,000 points like we were supposed to. You'll notice the targets reset instantly when the 10th target, and it continued like sending the score out. It was fine, so it did that immediately. And all of that's remembered too, by the way. And you'll notice that now we have extra ball and special, which are part of the original. So we got our knocker like you would expect, and then I could get my extra ball here as well. And now I'll drain and watch the. Let's watch the animation. So if you watch the. So you see how it's doing green. So it does an animation countdown, which I forget what games Gottlieb did. Can someone name some of the games that do animation during bonus EMs? I know I've seen it.
The ladder counting down.
It's like a ladder countdown, yeah. So it's kind of sort of emulated like that, exactly. So that's a good demonstration of the rule set. And as I said, I'll do a quick. And again, you can see it resets instantly, and we can knock it down a second time if we want to, and keep going on and on. And some other things, we animated when the target drops, flashes, goes into the purple state, all that kind of stuff. So with that, I think we want to. Do we want to? Yeah, I got 5 minutes. Okay. 10. Okay. So do we have time to show the bottom of the playfield, or should we do questions? What would? Thank you. So so you can see the controller here, and there is a status LED that sort of gives us some indication about what's going on in the game and stuff like that. There's another one down at the bottom as well. I didn't really talk about that, but you can see the connections are really, really simple. If you follow some of the wiring, like this is the cable that goes to our apron display. It's just 3 wires. You can see some of the RGB inserts here that you'll see. Each of the inserts. You'll see the custom board down here for the 5-drop target bank drop. And you'll see similar boards down here where the 10s are. And you'll see 2 different boards that are wired in series with each other. And then here's an example of like where we take off. This is the B relay. So I think a lot of folks are probably familiar with the B relay. If you've ever worked on a Gottlieb, I'm sure you've dealt with this one. And just 2 of those contacts are taken. That's it. Just remove 2 of those. We get 2 of the outer contacts. And now we know whenever the pop bumpers are getting asserted. So that gives us the information about when the pops are asserting. Very similarly, you'll see our stand-up targets. Again, this is another good example of you'll see the wires that are taped off to the back, and then you'll see the 2 connections to the stand-up targets. So that gives us when the stand-up target gets hit. You'll see a similar stand-up target connection here as well. And then some other places that you'll see where it gets stitched in is you'll see like these rollovers here. So if you take a look at those rollovers, you'll see again, some custom wires. The original stuff is tapped back here. You'll see how it's heat shrinked back, and then you'll see the original wire there as well. And then lastly, there is you'll see this is the RS-45 cable that you'll see, and that just sort of snakes down here. And then that connects down to the lower relay board. And now, once we have the relay board, you'll see the controller and the relay board. And you'll see that's doing a RG and B. That means that there's proper connection. Thank you, I got it. So, no worries. So you'll see the RG and B connector there. You'll see this is the status LEDs for those optos, which is last ball and also tilts. And then you see the connections here to the relay boards. So you'll see the 2 different relay boards. And if we were to do a rollover, for example, that's involved with that, you can see the LED flash. You can see the LED flash down there, with one of these relays that's getting actuated. And you can see a couple of the connections that basically connect. If you sort of follow it closely enough, you can see how the wiring connects to a couple of the Jones plug connectors. And you'll also see the cable down there. You'll see a cable down there, which is the one that goes up to the head and connects to the LM and N relay. So, but that's it. I mean, the rest of this game is all completely preserved. So I'll show you an example of like, so this time if you watch the score motor, so watch this. So notice I just did 500 points. Notice the score motor did not spin, but now I'm going to do a regular EM one. So there are still a few switch contacts that we left as EM connections, and you'll see the score motor spin in order to dispense that code. But if it's a solid state controlled, then the score motor doesn't need to spin for that. So. Oh, are they? Oh, thanks. Yeah, it's It is OCD, yeah. I've been accused of that in the past. Yeah, yeah. I think us OCD people know each other when we see each other in the field. So
I'm going to stick in one remark, revealing something I've never revealed before that I've kept secret for over 50 years. In the mid-'70s, Williams was thinking along these lines. They had a whole experiment of changing over to solid-state module by module, probably inspired by the way jukeboxes, if you might remember, from about 1968 to 1976, jukeboxes changed to solid-state module by module. And Williams had been thinking of that same thing on pinball, like let's do a credit unit that's just a modular credit unit, and then let's do a modular score display later, and then work in bit by bit. So this is very much in that spirit. So
yeah.
Steve Kordek would approve of what you're doing.
Fantastic. Yeah, I have a feeling if the Gottlieb guys were here, they'd approve of it too.
Yeah.
It was a nice way to kind of transition it, you know. I mean, it's the next one. Dick Hamill's doing the next seminar, by the way. I've actually implemented 7 games with his code base, so you know, I can't wait to see his presentation. I'm a huge fan of that. So if you have time, highly recommend you attend the next session.
And you'll be hanging out most of the weekend in the custom game room?
Yeah, yeah, absolutely. So I'd be happy to answer any questions.
If you think of other questions,
absolutely, get a chance to play it too, because you know, and hopefully it continues to work. Hopefully, I don't have any more relay failures, but you never know. It's pinball after all, right?
All right. Thanks very much, John.
Thanks, everybody. Appreciate it.